Hello everyone. Let's now move on to part 2 of module 2. Part 2 will cover covalent bonds, electronegativity, and electron affinity. Let's first go back to the topic on covalent compounds. Recall that nonmetals form covalent bonds with other nonmetals. Unlike ionic bonds, nonmetals can share 1, 2, or 3 electrons with a single nonmetal. This property allows nonmetals to form more than one covalent bond with another atom. Nonmetals can form single, double, or triple bonds to form covalent compounds. The number of bonds represent how many electrons are shared by the bonding atoms. Here are examples of single, double, and triple bonds. H2 forms when the lone electrons of hydrogen pair up to form a single bond. Hydrogen exists and is stable only as a diatomic molecule. O2 is also a diatomic molecule, and this is the form of oxygen that we breathe. In O2, each oxygen atom shares 2 electrons with the other atom. Note that this is possible because oxygen fulfills the octet rule. Each oxygen atom now has 8 electrons in its valence shell. N2 is also a diatomic molecule made possible by the sharing of 3 electrons from each nitrogen atom. Earlier, we learned that nitrogen has 5 valence electrons. It needs only 3 more electrons to fulfill its octet requirement. So by sharing 3 electrons with the other nitrogen atom, they now have 8 valence electrons. This form of nitrogen is a gas and make up most of our atmosphere. We can represent the bonding of these molecules using lines. H forms a single bond with the other H atom. Oxygen forms a double bond with another oxygen atom, and nitrogen forms a triple bond with another nitrogen atom. To complete the setup, we need to include the electrons in the oxygen atoms that did not participate in the bonding. The same goes with nitrogen. The type of covalent bond that is present in covalent compounds is a very important property in organic chemistry. The number of bonds create different molecules with different properties. For example, C2H6 is ethane, a major component of natural gas. It is a compound made of C single bonded to C and H atoms. C2H4 is ethylene, the compound that causes fruits to ripen. It has one double bond between the 2 carbon atoms. C2H2 is acetylene, which is used as a fuel and chemical building block. It has one triple bond between the 2 carbon atoms. Covalent bonds can be nonpolar or polar. In nonpolar bonds, the atoms have the same pull on the shared electrons. In polar bonds, the atoms don't equally share the electrons. One side is more electron dense than the other. Here are other examples of nonpolar and polar covalent bonds. In a covalent compound, when one atom is more electron dense than the other, a polar compound is created. Note that in a nonpolar compound, all the electrons are equally shared by the atoms. But in a polar covalent bond, one side is more electron dense than the other. This creates a polar covalent compound. Compounds with polar covalent bonds can form weak bonds with other polar molecules because of the electrostatic attractions of the free valence electrons. Molecules that are polar can thus form weak bonds with other likewise molecules. One type of weak bond is the hydrogen bond. The water molecule is the perfect example of hydrogen bonding. The unpaired valence electrons on oxygen attracts the positively charged hydrogen atom in another water molecule. This results in a linking of millions of water molecules. Hydrogen bonding is an important characteristic of the water molecule. The hydrogen bonds make water cohesive and adhesive. Hydrogen bonding is what makes water the universal solvent. It is the reason why a drop of water on any surface will retain its shape. Hydrogen bonds also allow water to move up or down a column, as in plant tissues. Hydrogen bonds also connect the various molecules that form our DNA and RNA and even proteins. Now let's move on to the topic of electronegativity. When an atom with a valence electron meets another atom, its attraction to the other atom's nucleus can determine whether the two atoms will form a bond. This attraction depends on factors such as the number of protons in the nucleus, the distance from the nucleus, and the amount of screening by inner electrons. The ability of an atom's nucleus to attract the valence electron of another atom is called its electronegativity. Electronegativity are expressed in values that range from 0.7, the smallest value, and 4, the largest value. When atoms with different electronegativity values meet, either of three types of interactions are possible. No electronegativity difference, a small electronegativity difference, or a large electronegativity difference. When the difference between the electronegativity values of A and B atoms is less than 0.4, a nonpolar covalent bond forms. When the difference between the electronegativity values of A and B atoms is between 0.4 and 1.8, a polar covalent bond forms. When the difference between the electronegativity values of A and B atoms is greater than 1.8, an ionic bond forms. The periodic table of elements can be used as a guide to determine how electronegative or attractive an atom is to other atoms. Electronegativity increases from left to right and from bottom to top of the periodic table. The element with the highest electronegativity value is fluorine. The elements with the lowest electronegativity value are cesium and francium. This means that fluorine has the highest tendency to attract electrons among all the elements. Francium and cesium have the lowest tendency. Elements on the right side of the periodic table have higher electronegativity values than elements on the left side. Given the following elements, let us arrange them in order of increasing electronegativity. First, we need to find out what their electronegativity values are. So for lithium, the electronegativity value is 1. Nitrogen has an electronegativity value of 3.0. Silver has an electronegativity value of 1.9. Bromine has an electronegativity value of 2.8. And barium has an electronegativity value of 0.9. So if we arrange them in increasing electronegativity, we would put barium first, lithium next, silver next, bromine, and finally nitrogen. Now let's use our electronegativity values to determine whether these compounds are nonpolar, polar, or ionic. Let's start with the diatomic molecule fluorine. We can represent this as fluorine single bonded to fluorine. The electronegativity value of fluorine is 4. If we get the difference between these two values, we get 0. This makes fluorine a nonpolar covalent compound. Now let's go to HCl. The electronegativity value of H is 2.1. That of chlorine is 3.0. So the difference between these two values is 0.9. This makes HCl a polar covalent compound. Then we go to CO2. CO2 is oxygen double bonded to C double bonded to O. The electronegativity value of oxygen is 3.5. That of carbon is 2.5. If we get the difference in values between this side and this side, we have 1. This would make this side of CO2 as polar and this side also polar. But because their values are the same, they cancel each other out. This makes CO2 a non-polar covalent compound. Then we have NaOH. We can represent it as sodium bonded to O bonded to H. The electronegativity value of sodium is 0.9. That of oxygen is 3.5 and the value of H is 2.1. So the difference between electronegativity values on this side is 2.6. On this side, it's 1.4. This side of NaOH is polar, whereas this side is ionic. But because this value is higher, that means NaOH is an ionic compound. Okay. Now we go to our final topic, electron affinity. What makes it possible for atoms to gain or lose an electron? The answer is energy. Electron affinity is defined as the change in energy expressed in kilojoule per mole of a neutral atom when an electron is added to it to form a negative ion. In simpler terms, this means the neutral atom's likelihood of gaining an electron. What is energy in terms of the atom? The energy of an atom is defined when the atom loses or gains energy through chemical reactions that cause the loss or gain of electrons. A chemical reaction that releases energy is called an exothermic reaction. A chemical reaction that absorbs energy is called an endothermic reaction. Energy from an exothermic reaction is negative, thus energy is given a negative sign. Energy from an endothermic reaction is positive, and energy is given a positive sign. The periodic table of elements can once again help us to determine an element's electron affinity. Electron affinity increases from left to right and from bottom to top of the periodic table. Each electron that is gained by an atom requires energy. When an atom gains its first electron, we refer to this as the first electron affinity. The first electron affinity is exothermic, so first electron affinities have negative values. By convention, The negative sign shows a release of energy. For example, the first electron affinity of chlorine is minus 349 kilojoule per mole. When an atom accepts its second electron, more energy is needed. This is a common trend for group 16 elements, such as oxygen and sulfur. The second electron affinity is an endothermic reaction. More energy is required to add an electron to a negative ion. So, second electron affinities are positive. Metals have lower electron affinities because it is easier for these elements to lose their valence electrons. Their nucleus does not have a strong pull on their valence electrons. Non-metals have higher electron affinities because they need to accept electrons. The valence electron shell of these elements is closer to their nucleus. Thus, it is harder to remove an electron and it is easier to attract electrons from other elements.
So that's the end for this week's module topic. The deadline for submission of Module 2 activity worksheet will be announced in Google Classroom. Thank you for listening.